Okay, so we can complete this by, so once again, that's what we have, the correlation between R1 and R2, we had it in this form. And we can make use of just one standard relation in the hypergeometric function of alpha, beta, gamma, c is also, you have this relation, 1 minus c to the power gamma minus alpha minus beta, gamma minus beta, gamma minus alpha, gamma c. So if you use this, if you apply this relation here, you can quickly see that it comes up to this. Now what is interesting, the final thing is to relate this to a result due to Uhlenbeck from, I think, in the 50s or something. So this gets related to the elliptic functions, and that's where I want to stop by just stating that result. As you may know, there are two kinds of elliptic functions. This is the elliptic function of the first kind. And this is the elliptic function of the second kind, integral 0 to pi by 2 square root of 1 minus k squared tau sine squared tau theta. Now, this result can be written in terms of this. The easiest way is expand everything as a series summation. And so I'm just going to state the results. It's too many terms to show here. So the interesting thing is you can show that the first, can be written as pi by 2 multiplied by 1 plus half the whole squared, k squared, then 1, 3, 2, 4 squared k4 plus etc. That's the expansion there. Here it's going to be, so in general, if you want to write this, so I'll write this. We can write this as summation, 1 plus summation n equal to 1 through infinity, the whole thing pi by 2 outside, then 1, 3, 5, etc., 2n minus 1, here 2, 4, 6, etc., up to 2n, the whole thing squared, k to the power 2n. That's the first hypergeometric function. So I'm going to call this 2. And if you bring in the second hypergeometric function, this is the first elliptic function, and the second elliptic function of the second kind is 1 minus k squared sine squared theta d theta. And this also has a similar expansion. Easiest way is just to expand this as a binomial expansion, and then again substitute the values for integral sine to the power 2m theta d theta. You will get this expression. So this term is the same as here, except that here there is a denominator, it's the 2n minus 1. And then the whole thing squared. So let me call this 3. And one can also expand this 1 as a series summation. So we already have so this, if you simply use the definition of the hypergeometric summation, for example, this will be 1 plus the minus half, the first term, multiplied by minus half plus 1 plus etc. minus half plus n minus 1, last term. This is twice from here, 2 times. Denominator is n factorial, k to the power 2n. There is a summation here, 1 plus summation n equal to 1 through infinity. If you rearrange, I'm going to leave the details here. This will turn out to be n equal to 1 through infinity, 1, 3, 5, etc., 2n minus 1. Same as there, 2, 4, 6, etc., 2n. The whole thing squared to the power k squared, k tau to the power n over 2n minus 1, the whole square. And here is the interesting thing. Now, if you have three series in front of you. One is this series number 1, and 2 and 3. So if you manipulate this, which it's easy to show the following result. So this will so this will come out to be E R1 R2 will come out to be sigma squared. So you can write this series in terms of these two series. So this will turn out to be, so we have this whole thing multiplied by pi by 2 multiplied by sigma squared. Here, this is equal to, and notice that these things also have pi by 2 multiplied by sigma squared. So if you substitute all this, this will turn out to be sigma squared multiplied by 2ek squared. This is the second elliptic integral minus 1 minus k squared multiplied by the first elliptic integral. So I'm going to rewrite it here. So that's the interesting result, and I believe this result is due to, this particular relation is due to Uhlenbeck. So remember, R1 is R of t, this is R of t plus tau. So of course this is coming from a Whiteson stationary process. The whole thing is in terms of tau. And if you want, so this is the in terms of the first and the second elliptic integrals. Otherwise you have the power series expansion there. So finally I just want to make one point that if you find the correlation between correlation coefficient between R1 and R2, that will be of course ER1 R2 minus ER1 ER2 over square root of the variance of R1 and variance of R2. So this will turn out to be because the variance is for Rayleigh, so you substitute that, so the expression will turn out to be, exact expression is like this. All right, so this is again a series expansion, but the interesting thing to see is, remember if you recall earlier from the joint density function, if k squared tau was of course rho squared tau plus gamma squared tau. So this is k squared. So if you had substituted the and the joint density function turned out to be what? Something like this. So So notice that if the two random variables are independent, in other words, if k is 0, you can see from here R1 and R2 are independent. Because if k is 0, this splits up, this is 1. So so if the two random variables are independent, of course you can, so it goes both the ways, that's the whole point. If the two random variables are independent, then k is 0. Conversely, if the correlation is 0, you can see correlation is 0 means k has to be 0, k tau is 0, and k tau equal to 0 means rho and gamma are zeros. So if you go back, you can clearly see that from here you will also get this to be fr1 multiplied by fr2. So the moral of the story is if the two random variables are independent, then k is 0. But conversely, if they are uncorrelated, then k is 0, and conversely, and the two random variables are independent. So here is the joint density function when they are not independent. So in general, this is not true. This is the joint density function, and k is this quantity, which is like a correlation function. And the correlation between R1 and R2 can be expressed in terms of k, but it's an infinite series. And if you want just the correlation between R1 and R2, not the correlation coefficient, just expected value of R1, R2, that also can be expressed in terms of the elliptic integrals of both of the first kind and second kind. So here is a communication problem where it involves the elliptic functions, and that's what I thought the derivation will be interesting. Thank you.